Great event, Amsterdam, perfect city.
Move back to the future.
So good morning to you all. Mark Dunnet from Embedded Pro. I'm a experienced professional in embedded systems. I have a long 20-plus year career in embedded systems with Motorola and NXP and Freescale, where I've been an application engineer solving my customers' problems in the embedded space. In May, I left to set up on my own, so I'm a consultant, and I work with partners to solve their real nitty-gritty problems. So you'll find me on LinkedIn. There's my email address. If you go onto the mcuoneclipse.com blog site, you'll see me blogging and video blogging on that site. So let's get going, and I thought I'd challenge you to start with. So my topic is embedded low power and other lies. Now, I don't want to mislead you. I'm not saying that the semiconductor vendors are trying to mislead you or lie to you. They're just not presenting the information that you need in the way that you want. So when you look at a chip and it says, 100 milliwatts per megahertz per core mark, you know that they're not giving you the full truth. It's more of a marketing number. So the presentation is really about things that I've found about the embedded systems that we're using, how we can learn from other people's mistakes, and how to optimize our systems for low power. The cellular connectivity, Wi-Fi, Bluetooth, maybe the GPS antennas. And of course, really by definition, those radios tend to be higher power. So we might be talking 200 milliamps, maybe a peak current of an amp in some of those radios. Bluetooth, much, much, much lower, in fact. But we've got a power challenge to meet. And of course, as you know, we're meeting that challenge just by switching the power on and off to the radio modules. If we're going to switch power off to the radio modules, we need to consider how we're going to wake up the system, how we're going to turn those modules back on again. And there can be many triggers in our embedded systems to wake up. I show some here. Hopefully we can wake up from a low battery alert. Hopefully we can wake up with a temperature change or when a fault condition occurs. But if we look at the architecture, of course, it's those sensors that are powered up all the time, and they're triggering the microcontroller to wake up. Maybe the microcontroller is powered all the time in an ultra-low power mode, and then requires an internal timer to trigger it to wake up every 15 minutes, for example. So it's that microcontroller which is really the power use case. That's likely to be on all of the time, and whether it takes an amp, unlikely, or 100 nanoamps is going to make a big difference about the power and the battery sizing. So the question comes down to, what size battery do I need? And of course, we know this, but what we're actually saying is, how many service calls do you need to put in to send someone out to fix the system because of a battery? Or if you don't have a team of people going out replacing batteries, we're talking about how often does the user need to replace the battery, or how often does the user need to recharge the battery? And if you've got the battery scaled wrong and the battery needs recharging every 3 days, you're going to see reports on kind of forums about, this sensor's got a short battery life. You want to be the ones with I can't believe this sensor, it's got the best battery life I've ever had. So we saw the ThingStream button earlier on. That's got an 800 milliampere hour battery, and to make that real, that's 800 clicks, 800 connections to the server. So it's a number to have in your mind, 1 milliampere hour per connection. It's a really good kind of scaled number to have in your minds as you're developing a system. 10-day battery life for that button on a 15 minute per connection. Okay. So we have to scale the battery, and we have to understand what the microcontroller is doing and its low power modes. And a convenient way to do this is to profile how much current the microcontroller will be taking at different times. Hopefully it's in an ultra low power stop mode for most of its life. But we're going to need to know what the manufacturer of the chip will claim for that ultra low power stop mode. So we could just build up the area under this curve by knowing how long in each mode and how much current, and we can calculate the milliampere hours per second or milliampere hours per microsecond. Of course, it's a little bit harder than that because we need to have a reference for these current consumptions. We go to the chip datasheet for that. But it's not very clear in the datasheet what those numbers actually mean and in what use cases they've been done. And of course, the other thing that we need to know is how long is the microcontroller going to be in these different modes? Well, I know that my node's going to wake up every 15 minutes. So that's 15 minutes in the stop mode. But how long will it take to wake up? How long will it take to work out what the sensor's doing? How long will it take to send the packet off to the cloud? So these things are quite complicated. And we do get into, if I can make that work, try that one. We do get into a little bit of pain about the units that we're using, because Tom will talk about batteries in milliamperes per hour, but these types of charts are kind of microamps per second. So it's often easy to get an order of magnitude wrong in our calculations. But of course, it's a bit harder than that, because we've got all of these different kind of modes that the microcontroller is running in, different kind of frequencies it's running at, different peripherals turned on, which are really dynamically affecting the current consumption. And we have to work out the area under the curve for all of that chart. It's a minefield and practically impossible to get right. We have to get it right. We have to get it right, because if the battery is underscaled or overscaled, the battery life of the product will be too short, or we'll have put a battery in that the BOM cost is too expensive. And no one wants to be recharging batteries or sending out service engineers to fix these problems. So here's the first problem that we see, that we take the microcontroller into a run mode and we think, okay, 10 milliamps in run mode. But actually the area under the curve isn't quite rectangular, so we get this kind of overshoot and then undershoot and then a tail off as the power comes off. Well, okay, that's physics, and that's probably the power supply design making that happen, but just a simple rectangular waveform isn't providing us enough detail to actually quantify the battery size, because we have to allow for all of that additional work that we weren't really expecting the battery to need. And look at that long tail. Okay, if we're waking the microcontroller up, powering it down, waking it up, powering it down on quite a fast cycle, it may be that that long tail, we're actually sort of stepping into that, and we wake the microcontroller up before it's really got into the low power mode. That's going to have an effect on the battery life as well. Okay, and then here's the real problem, is that these microcontrollers are so complicated nowadays with so many different kind of low power modes. Me as an engineer sitting at the desk thinking, right, we're going to spend 15 minutes in a low power mode. Well, yeah, which low power mode? So we go to the reference manual, and the reference manual says, very low leakage stop mode 3, and stuff about what the microcontroller can do in that mode. And you know, I have to do the design of the system and understand all these low power modes before I can do my graph of kind of what mode I'm going to be in. It's fiendishly complicated. So that's an approximation that we have to take, which is, I'm going to guess a stop mode that might be relevant. But down the line, if you find that it won't wake up on the sensor in that mode, or all the RAM contents were lost, you know, we have to do more work to wake up. We have to go back and rescale our battery. Okay. Well, here's the first lie, okay? Here's the first misleading information from the supplier, okay? Don't believe the stop mode currents, and don't believe the maximum currents that they put in the data sheet. This is a wafer, so let's talk about a 90 nanometer process. And here's a chip, there's a data sheet from a 90 nanometer process. And look, well, 1.98 microamps in the very low leakage stop mode 3, whatever that is. Well, 90 nanometer is a very, very leaky semiconductor process. So as the temperature rises, the chip leaks and leaks and leaks. So if you do your design based on this number, 2 microamps in stop mode, that's fine at 25 degrees, but definitely not at 105 degrees. If your product works at 105 degrees, speak to Tom if that's actually real for an operating temperature for a battery. And what the semiconductor vendor is going to do is they're probably going to give you some typicals. If we go back, they're going to give you some typicals, which we can ignore because they're not relevant. And they might give you this maximum figure. Well, that's just not helpful. So if you're specifying a microcontroller, you're looking for the vendor who's taken the time to look at the intermediate temperature ranges, something a little bit more practical, say 50 degrees, to give you a realistic number, because that might be the most relevant maximum and not this one. So don't believe maximum values. And don't believe run values either, because we need to know how much current the microcontroller is taking in run mode. Well, here it is. Running while one loop in flash, yeah, flash, good, we've got to run for flash, this particular frequency, da-da-da-da-da-da. Okay, 2.87 milliamps. Okay, I can live with that. But here's the lie, because when we're running a while loop, the chip has actually turned the flash memory off, because it's got that instruction, it can just run that instruction from an internal cache. So the more relevant number would actually be that one. And this data from a manufacturer's data sheet is actually saying the flash memory array takes current that you haven't allowed for. So of course, if we're speccing a battery, that would be the most relevant value. Maybe that one's probably a little bit extreme, but not so useful. So it's all there, it's all published in the data sheet, but they're just not making it very obvious about what we're actually going to achieve. Okay. Well, production tested and characterized. So the data sheet will say we probably don't production test that operating current that you're going to base the whole of your business case on. That will be a characterized value. What does characterized mean? It means the very first wafer that came off the fab when it was being hand optimized, and your physicist is optimizing the process day by day as that first ever wafer is grown with no optimization for yield and don't care about how much yield I get from my wafer. That precious, very carefully brought up little infant is the one that will be used to characterize the sleep mode currents. So what's published in the data sheet was true for that first ever wafer. It may not be true for what you buy from EBV for your product. And then here's the real kicker. So from that first wafer, we measured our stop mode currents, and we worked out a kind of distribution of kind of the values. And what we published in the data sheet is plus or minus 3 times the standard deviation. Just if you need a little refresher on that, here's our standard deviation curve, and 3 sigma is here. So not every unit that you actually buy will meet that characterized value. How bad does it get? Well, 1 in 370 units may not meet the datasheet value by definition, because the datasheet value is a 3 sigma value. So you've scaled your battery based on datasheet figures which were characterized, and the figure in the datasheet is published to be the best possible kind of nicest value that's kind of makes you think that the microcontroller is kind of, fantastic at low power. It's not something you can scale a battery on, because by definition, 1 in 370 units are going to require you to send out a service engineer to change the battery. Or, 1 in 500 units are going to have a much lower battery life than what you expected it to have. Okay, this is bad news, but this is kind of reality for anyone working in IoT and embedded microcontrollers. So what do we do? What do we do? Well, I think the advice I can give you is whichever microcontroller you're using, the supplier will have some power management software that enable you very quickly to move in some of these low power modes. So I would recommend that you or someone actually tests the microcontroller in a number of different use cases. Rent an environmental chamber if you need to do that, just to kind of look at the realistic kind of temperature profile for your system. And there should be a piece of software you can quickly run on an evaluation board to put the part into the different low power modes for you to actually go measure. Just be careful though. Here's an email I had with an ex-colleague about demonstrating low power modes on evaluation boards. There we are, it's kind of sub 2 microamps was the target. Well, we have to use this particular version of silicon on this particular version of development board. And oh, by the way, you have to take off these jumpers. And if you want to measure it accurately, then you've got to take off the accelerometer. And there's this kind of level converter on the board that somehow takes 70 microamps. So you have to do a little bit of work on the supplier's evaluation board to even get to their figure, which they were lying about in the first place. It needs some work to get there. Okay. From an embedded point of view, then power profiling tools are available. So whilst you're doing your software debug, some probes, and here's my friends at Sega, they offer debug probes that can actually measure the current that the board is taking whilst you're in a debug session. And that's great because you can actually see where code is running and how much current the microcontroller is taking right there and then. It gives you a very good feel for how much current the micro is taking. Okay. You don't need an expensive probe. On a supplier's development board, they've got a jumper that can be put in place, and their free development environment has got this power profiling tool. And the same as the expensive probe, whilst the software is running, we're able to measure how much current the microcontroller is taking. And here's a test I did on a Bluetooth radio, and we were just changing the output power and looking to see how the current consumption was increasing as the output power was ramping up. With the idea being that when we're pairing and we want to be physically close to the node, that we have the part in a low power mode, low power radio mode, and in that case we saw an average of about 1 milliamp when we were advertising. So tools are available. The developers, your software engineers will probably know about these tools, but it's a really good way to get to grips with what's going on. Okay. One problem that's often overlooked is the transition current. So we're in a sleep mode, and we want to transition into run. So in our mind, we think that takes 0 kind of seconds. But actually, probably there's no oscillator running in this mode, and to get the chip up and running requires an oscillator to start up and kind of generate some clocks to transition the logic into run. And this adds kind of a hidden penalty, which is not always obvious. So having a grasp of that is very useful. And what does that mean? Well, here's a datasheet figure. So to go from a particular low power mode into run, it can take nearly 200 microseconds. And of course, while you're doing that transition, the chip is likely to be taking the run current, not the sleep current, because here, all the logic's powered up, it's starting to want to access flash memory, the clocks are running, so it's kind of in the high power mode. And if you're waking up on a very, very fast interval, this hidden phantom current can be quite significant in the design. Okay, so here's a tip. I recommend when you're up and you're working, do your work as fast as possible and then get back to sleep again. It works in your life, it works in an embedded system. So here we are, we can show area under the curve. It's actually more efficient to get up, run at 48 megahertz and then get back to sleep again than running at, say, 8 megahertz. And that's a factor of the non-linear current versus frequency curve for the chip. The chip's going to require a certain amount of current just to run the chip, and then the dynamic current connected to the clock means that running faster, that area is always going to be lower than that area there. So that's a good tip. Run fast, get your work done, back to sleep as quick as possible. Of course, in an IoT node, you've got the connection to the server. So that dialogue is going to take a fixed amount of time, but you may be able to nip back into a doze mode or come back into a lower power mode just whilst the connection is being established. Okay, just a word, and maybe Tom will talk about this in a moment. Of course, just check the peak current that the system is taking when you're running as fast as possible, because that current may be in excess of what the actual battery that you're using is able to take. Okay. And then there's the topic of hardware acceleration. As you look at microcontrollers, ones that have come out in the last 2 years, they're starting to become very, very, very complex with lots of hardware acceleration. Here's one that I know and I've been blogging about, and in particular, you've got these two hardware blocks, a DSP accelerator and a cryptographic engine. The power quad DSP accelerator, its job is to offload DSP code, FFTs, filtering, even sinusoidal functions or square roots, inverses, to offload it from the core and run it on the DSP accelerator. Without the accelerator, you have to do it all in software, and of course software requires energy from the battery. So this is a square root example from ARM's Synopsys DSP library. So your software engineers are probably using this if they need to do any DSP functionality. So got our example, and we call the ARM Synopsys DSP function. Using the accelerator, exactly the same function call, but under the hood, there's a modified library from ARM, which is using the power quad. So instead of going to software, this function call is now sending this algorithm into the power quad, and that's doing it in hardware. Software can go to sleep and wait for that to complete, or software can get on with other tasks. The effect of that is that, of course, it's hardware acceleration. So it's massively, massively faster to compute some kind of DSP algorithm in the accelerator than it is in the core. So we're just comparing. That'll do. So we're just comparing the cycles to implement some algorithm, and comparing it against doing it in software on the chip. And something astounding like around 512 point FFT, so it'll be a real FFT, taking, a millisecond running in software, and 36 microseconds running it on the power quad. Of course, the intention of the power quad and these accelerators, whether it's DSP or cryptography, is to get the algorithm completed as fast as possible and get to sleep as quickly as possible. So when you're doing kind of filtering on the edge or kind of machine learning on the edge, these DSP algorithms in hardware are a really, really convenient way to get a lot of work done at the least possible current consumption. Of course, there's an adder for the hardware block that's doing all of this kind of accelerated function. But that might be 5 or 10 milliamps compared to the chip running at 48 megahertz for an extra millisecond or 2 milliseconds, where instead you could get back to sleep again. Area under the curve, always lower with the hardware acceleration than doing things in software. Okay. If you can get to sleep 10 times, or 20 times, or I think this one here, 40 times faster, I can only improve the battery life of the product. Okay, so embedded low power and other lies, not really lies, just misleading information. So let's look at some questions. To find out actual battery consumption, do you mostly measure on an actual working board with running firmware, or also model it based on hardware datasheet? Actually, we would use both. There would be a time at the beginning before we've actually got to hardware where we're going to be doing some metrics. We're going to do a model, often a spreadsheet. Often the supplier's got some tool that they'll offer you to help you make that calculation, just to get a feel for the scale and the type of current that's going to be available. And that gives me a kind of go, no-go decision. Or we might have to go into other low power modes to kind of reduce the power consumption as much as we can. And then once you've got that decision, okay, this part looks okay, then the only thing you can do is develop a customized low power board which has been optimized for measuring low power, and then actually do some real environmental tests to see what happens in this particular software, in these particular currents. And that gives you a feel for that particular chip. And now you've got to make 1 million and hope that that particular chip was representative. The semiconductor vendors will be happy to share. The semiconductor vendors will be able to share some of their characterization data to give you a feel for how these curves look over temperature. In asset management, is it okay for sleep mode, but for live tracking, how can we increase battery life? This is a tough one, okay? So it depends how we want to wake up the unit. We want to be in low power mode all the time, as much as possible. But of course, if the unit is moving, if the unit is, moved when it should be on a, in a dock, in a container, and isn't expected to move, we want to be able to trigger a wake up. Now we need some probably analog design to design the kind of circuit that's going to help us wake up on the sensor, but take zero current. That's not always easy with some sensors. A gyroscope, kind of micro machine kind of gyroscope, it's going to take more current than you could possibly want to have awake all the time. We were talking about this last night. If you've got an active key for your car, sits in your pocket, and you walk up to your car door and you open it and there's this communication, we have this fear about the relay attack where the key fob is in your kitchen and someone stands with a GSM system to read the key fob and relay it to your car. Cars are stolen every day with that method. So the way around that is to add a very cheap low power accelerometer into the key fob. And if it's sat on your kitchen table overnight, then the key fob goes off, won't accept any kind of communication over the low frequency that the key fob is using. When you have it in your pocket and you're walking to the car, This is vibrating as you're walking, and that wakes up the key fob. And when you get to the car, it's ready for that dialogue with the car. Oh, how much longer? Better life in real experience. It's always worse than you worked it out to be. You know, as you saw, the models, the data that you get, the kind of, this is what my curve is going to be like, it's always worse, always worse. Which is great for Tom. Where's Tom? Because he can provide us a larger battery to manage that. Given the low complexity of IoT applications, would it make sense to run the thing on an Fpga altogether, possibly with a soft-core microcontroller and dispense with the embedded system as well? Maybe, yes. At least with a soft-core Fpga, you're in total control of kind of what that module is doing. If you buy a microcontroller with a hardware DSP accelerator, it's great if you need the hardware DSP accelerator. You could probably turn it off to reduce the current consumption the micro takes, but it's always there, and somehow you're going to end up paying for it. So the benefit of an Fpga approach is you can massively optimize what the system is doing to suit your particular requirement. You're going to need RAM, which you probably get a RAM cell in your Fpga. You might need some flash, so you're going to have an external flash memory. Don't underestimate how cheap these external flash memories are. Great. Don't underestimate how much current those external kind of quad spine memories actually take when they're up and running. So Fpga, yeah, you're in control. Now you need 5 software engineers who are doing the Fpga kind of design in Verilog to make the system that you're trying to do. So to conclude, we're trying to scale the battery. That's what we're trying to do. We're trying to make certain that our system has the life in the field that we need it to have. The microcontrollers are really important. They're part of the battery life discussion. But actually, doing the kind of design, roughing it out in in design before you actually go to real unit to test is fiendishly difficult. Don't believe what you're told by the semiconductor vendors. Ask them for clarification, more data. Ask them for supporting information to help you use the microcontroller that you've selected. So I hope that was informative. You say, God, Mark, that's a bit cynical. I'd say, I maybe have some experience, and I've seen all these types of things before. The last thing I want you to do is send out a service engineer to a desert somewhere to replace a battery because somewhere along the lines, someone wasn't telling you the full truth. So with that, I'll hand over to Tom, and he can come and talk about batteries.